Right, thank you. I would like to thank the organisers for the chance of giving my talk here today. And as it was said, I'm also going to chair this session. Now, I can see from the programme that the organisers have had some difficulties in getting all the speakers here. So, as we're going to have a mixed bag of talks these next couple of hours, I would encourage the speakers to maybe not do them as detailed and with as many abbreviations as they would to a normal specialised audience, but rather make them interesting for a broader audience so we can have all some learnings going home from today. And with that, I hope to set the tone today, but let's see how it goes. So, I am with a company called Novozymes. I don't know how many here knows of Novozymes. How many? Could we just have a show of hands? How many here have heard of Novozymes? That's actually quite interesting because we are the biggest producer of enzymes for the industry. In terms of we produce the largest amount of recombinant protein in the world. And we do that mainly for bioindustry. So I can see I have to call my marketing department in order to get some more flyers out. We like to see ourselves as an innovative company. We're about 6,600 people worldwide, based in the US, in India, in China, in Denmark, where I come from originally, hence the weird accent. And we always look for good people within this industry, so please check out our website going forward. Today I'm going to talk about a small niche of that company called the biopharma. We are originally a company that was together with Novo Nordisk, which is a huge biomedical company producing insulins and things like that. And we were divested for about 15 years ago now. But we took a bit of that with us in terms of doing proteins for the pharma business, but not actual active pharmaceutical ingredients, but rather something to support the function of active pharmaceutical ingredients. So today I would like to talk about using albumin for improving the function of various active pharmaceutical ingredients. And I'd like to touch upon something which would also hit your small molecule, and that is that small molecules are usually quickly cleared from the human body. So for instance, if you take insulin used in diabetes, that has a half-life of about 5 minutes, 5 to 8 minutes depending on who you are. That means having only had insulin, when you had a meal, you would have to inject yourself every time in order to have insulin present to control your blood sugar level. And what usually happens when you use peptides or small molecules is that in order to have a period where it's actually active, what happened to the pointer? No, it's gone. I haven't got that long arms. So in order to have an active period for your API, which is sort of the yellowish in the middle there, you need to add enough peptide or small molecule into the bloodstream that you actually sometimes reach the toxic levels, then it quickly drops down because it's removed, then you have its ineffective dose, and then you fall below a certain threshold where it's no longer active and you actually have an ineffective drug in your bloodstream. And most of actually the side effects you see are usually from this red at the top where it's suddenly you kick up the dose in order to get in there and get an activity. So what you rather have is something along that green line where you can inject up to the effective level, but then you have a slow loss of your API going out of the system. So this is where we come in. We like to think ourselves as having a half-life extension technology that can enable people to do that with small molecules. Oh, cheers. Here we go. So this is, you have your injection, the peptide goes up, but it's actually too high a dose, you have side effects. Then it goes down, you have an effective dose here, and then it drops further down and you have an ineffective dose. Reality, you would like probably every week or every second week if you could, inject and slow decline, new inject, slow decline, and so forth. And there are drugs out there on the market where you can actually get this effect these days. But of course, some are suitable for some systems and some are not. So the molecule we suggest to use is albumin. Now, when I went to university 20 years ago, albumin was a fairly boring protein. It was just there. It actually constitutes the most, it's 40% of all the protein in blood, and it's involved in a lot of small things. It removes impurities, it brings toxins around, it gives the pressure to blood, stuff like that. But actually, if you're albumin deficient, you don't have any pathologically signs of it. You can actually live without albumin, which is, of course, a bit boring when we produce albumin and we like to sell it for something more. But it has a lot of properties that we can use. It's very soluble for ones. It's very resistant. The one we have is has a shelf life, of 5 years. You can keep it at room temperature for 3 years and nothing happens to it. It's a very strong protein, and it has a low immunogenicity, which is a nice thing when you want to add things to it in order to bring that into the body. Now, the reason why this is interesting for increasing the half-life is because albumin has a very long half-life in your bloodstream. It has a half-life of 19 days. Now, compared to insulin, we've had about 5 to 8 minutes. The reason for it to have this is actually down to 2 things. There is size, and that is that it's not filtered out in the kidneys, and this is often what happens. This is the main removal of impurities and small molecules in your blood, that is that they will go out through the kidneys. The other bit is something that's fairly new, about 15 to 20 years, is a neonatal Fc receptor. And that actually does that your blood is recycled. So blood is sampled all the time by your epithelial cells, and that is done in order to take it in, and then whatever gunk is in there is removed and degraded by the lysosomes and recycled. Now, things you do not want to have degraded will then be recycled, and albumin does this, but IgGs, for instance, also does this. So your immune system is also having this protective effect by the body. You have some of these FcRn receptors that sit here, and as the pH drops in these small vesicles, the albumin and IgG will bind to these Fc receptors. So when they open up, and you then, whatever goes off to be degraded, off to the dump, the rest that binds to the inside are rescued and go back to the surface and go back into the bloodstream. So albumin is not lost through the kidneys, and it's not lost by this continuous cycling of blood. And actually, we have made albumins where we knocked out the ability to bind to this FcRn receptor, and their half-life goes down to about 9 days. They lose about 60% of their half-life, and that simply comes from this recycling. You can then imagine, as your IgGs or your albumins, they become degraded because of what they experience out in blood. They can become oxidized, they can become glycosylated, stuff like that. They will no longer bind to the Fc receptor, and they will go off to degradation and recycling. That's how the system works. So we propose to bind albumin to small molecules or peptides for increasing half-life. And there's already been one drug marketed with this, and that is a GLP-1 fusion to albumin, which has been made by GlaxoSmithKline and came on market last year. And that is for diabetes, and it extends the half-life for the GLP-1 and makes you only have to inject yourself, I think it's every 1 week or something like that. So making it much more easy to adhere to your regime in order to fight your diabetes. And we have other things coming along. Now, the problem with binding something to albumin is that you can't, what we find is that we do not have the 19 days anymore when we actually bind things to it. So the one I just showed you before with the GLP-1, I think it has a half-life of about 5 days compared to the 19 days. And that's because we no longer have now just albumin, we have albumin with something on it, which makes that the body does not recognize it as purely albumin, which means that it gets a lower half-life. So ideally, one could think, well, if I could increase the half-life of albumin further, then I could also bring the half-life of my albumin plus drug higher. And that is what we have done then at Novozymes Biopharma. We have improved the half-life of albumin in order to improve the half-life of albumin plus your API. And just to have one small example of that, we have in one position, this is just one amino acid, and an albumin has 585 amino acids. Just changing one amino acid can change you from native sequence, so this is normal albumin, and then change that to different amino acids, and then you get a stronger affinity for the FcRn receptor, and you get a better and better binding. Just one other position B, you can actually kill the binding to the FcRn receptor, making these null binders that I talked about by simply destroying the ability to bind to the FcRn receptor. And just to show how that works, we've made some that uses more than just one amino acid, up to 5 different substitutions. And the one with the one amino acid was the 98, the brownish bar there. And as you can see, we can improve the relative binding to the FcRn receptor further and further and further, prolonging the half-life effectively of the albumin in the system. So how does that translate into in vivo pharmacokinetics? Because as we also heard earlier this day, mice do not resemble man that much. It would be nice to work with cells. Typical people start with rodents when they do medical studies, and moving further up. Now the trick with albumin is that because it's human albumin, and we would like to make medicine for human and not for mice, the market's not that big, I imagine, we need to do something that resembles man more, and I'll come into more detail into that later. But what we've done is that we made a double transgenic mice, because we find that the mice albumin and the mice FcRn do not correspond very well with what we find in more human-like models. And of course you can go all the way to primates, but these are expensive, and a lot of discussions around using primates for medical studies as well. So I'd like to use those as little as possible. Now the problem is that, and this is a bit techy with the numbers, but the point is that human and rat, for instance, albumin, has a half-life. So human albumin in a rat model has a half-life of about 15 hours, whereas rat albumin in a rat has about 2 days. And that's because, and this is then with mouse, but it's more or less the same with rat, is because mouse albumin and rat albumin bind stronger to the mouse FcRn receptor than human does. And therefore it's outcompeted, especially when you do studies when you inject a small amount of albumin to look at, and there's then this huge amount of endogenous mouse or rat albumin, which will outcompete the binding of the human albumin. Further to that, actually, it's found that the mouse albumin binds stronger to the human FcRn than human albumin does. So you can't even just knock out just the FcRn, you have to knock out both of them, because otherwise the mouse albumin will outcompete the human albumin still for binding to the human FcRn. That's why we make these cokey double knockout mice. So, and that also means that, and this is then of course a bit of a challenge, that when you try to tell people that we are trying to make a drug now which will give you 1-2 weeks half-life in man, you have to start out with a mouse study where you come out with a half-life of maybe 15 hours, which is not very impressive when the mouse albumin on its own can do 2 days. And that's simply because of the species difference that you face working with human albumin. So this is shown here. We have the null binder, the the battery's gone again. Oh, good. The V888, which has about 19 hours in mouse. Then we have non-native sequence albumin, slightly better, but really is a null binder in mouse. And then we have one of these improved binders, which then get up to about 31 hours in mouse, but still nowhere near the 2 days you would see for just endogenous mouse albumin. As you move to primates, you get a much better half-life. So now native sequence albumin, human albumin in a primate has about 140 hours. And then you can move up, 98, that's just one amino acid that's been changed. You get about 260, and then we have different variants that all around, clusters around 330. So we have a half-life of about, And then you can see going from primate to man, you normally have a factor of about 1.5 to 2, sometimes 2.5. So you can actually start talking about maybe have a monthly half-life in man of these different albumin variants. And we have one example from one of our collaborators where they actually put a SCFV and a scaffold on the end of the albumin as a fusion, and there we've got a half-life of about 11 days in primate again. So in man it would be even longer, presumably. So how to put things onto the albumin? There's two ways of doing that actually. If you have a natural peptide, so that's linear, only natural amino acids, you can fuse it onto albumin. And you can fuse it C-terminally, N-terminally. You can maybe have, if you need both the C and the N-terminal to be active, you can put them on either end of the albumin or both ends. You can put linkers in if you need to have distances in order to bind to receptors. Most of these have been done, and most of them are published out there. The other way of doing it is to do it chemically. So if you have a cyclic peptide, or if you have a peptide that uses non-native amino acids, or you just have a small chemical entity that you want to have a longer half-life of, you can chemically conjugate it to albumin. Because albumin is special in that it has one free amino acid, or one free thiol, a cysteine, in position 34, which is the main contributor in our bloodstream of reducing equivalence. So that is sort of a scavenger for oxidative species, the free thiol of albumin. So it's designed to be a free thiol. So that means when you purify albumin, you get the free thiol readily with the albumin. So we have about 95 to 100% of free thiol in our albumins. As opposed to if you try to modify in a free albumin in a protein, often you have to reduce that protein, finishing the purification, because that site will not have been optimized for having a free thiol in it. So for that you can use malamide chemistry, or there's heaps of new chemistries out there for binding to thiols that you can utilize. And thereby you can chemically conjugate to the albumin. We do this with partners because, as I said earlier, we make enzymes, we make recombinant proteins, we do not do chemistry. So we have a collaboration with Biologics down in London, and Almac up in Edinburgh to do the actual work. We don't do chemistry ourselves. So one question could then be, fine, now you bind something to the albumin, but what happens to the ability to bind to the FcRn receptor? Do you destroy that in any way? And it's a fair point. So we've done that with a couple of things. We put endostatin onto our albumin, and as you can see, the ability to bind in vitro to the FcRn receptor of both mouse and man is retained after the conjugation. So we have the same affinity before and after conjugation. We also have a cell cycling assay, again trying to avoid using as many animals as possible. And there we get more or less the same recycling effectiveness of the conjugates as we do from the native or the unchanged albumin. So endostatin, which is used in cancer treatment, we've tried to fuse that on and see what it does for the half-life. Again, endostatin is a fairly small molecule that you have to dose repeatedly in order to be active in a regime against cancer. But putting albumin onto it, you can see we have native sequence albumin here. If we conjugate to the native sequence albumin, we have a slight degree in half-life, but then we have these variants with the stronger binding to the FcRn, and we get a better and better half-life, even for the conjugates of endostatin. We've done it with exenatide, which is a drug that's used against diabetes. And again, binding exenatide to the albumin does not really change the ability to bind to the FcRn receptor. If you do it in wild-type mouse, you can see that the native sequence with exenatide has a half-life of about 11 hours. And then as you use it better on albumins, you get up to 15 hours. It's still not great, but this is because, of course, it's a wild-type mouse. It's not trained, so to say, to bind human albumin, so it's what it would expect. But still, we do see an effect of it compared to the normal exenatide. So, and this is a bit messy, I must admit. It's a bit, I'll try to go through this in steps. So, these are mice that has diabetes. You can have these models. And if you just leave them to live normally, they will have fairly high blood sugar level, and that will be the black ones up here. And if you just give them native sequence albumin, you wouldn't expect anything to happen to the blood sugar level. And it jumps around up here with a fairly high level. Then you can give them exenatide, which is a GLP-1 activator, which will then lower the blood sugar level for as long as the exenatide is available in the bloodstream. And those are these diamond shapes here. You can see they go, it goes down, but then it goes fairly quickly up again because exenatide is quickly cleared from the system because it's a fairly small molecule. But binding exenatide to albumin improves the half-life of it, and therefore you should also see depression of the blood sugar level for a longer time. And in fact, that is what we do. So for the native sequence, which had the half-life about 11 hours, you see a decrease in the blood sugar level for about maybe 50 hours, whereas when we bind it to the version 354 of albumin, which has a slightly longer half-life, or almost 50% longer, we see that the decrease in the blood sugar level now is good for about 80 hours. And that means that, of course, you still have the effect of the exenatide, the pharmacological effect, even though you conjugated it to the albumin. Right. Just briefly, at the end of what we do and what we cannot do, so to say. So what we normally do with people when they come along and they say they have an API, they want to see whether half-life extension works, we do proof of concept study with people because we are not a medical company, but we will help them introduce and make the first studies in mice and maybe monkey. And from there, we can utilize our toolbox of using assays for FcRn binding and cell assays. We do yeast expression of the albumin. Albumin has 17 disulfide bonds. It's very rigid protein in that sense, so you have to do it in yeast. You can't do it in E. coli. We do conjugation technologies with partners, and we have these double knockout mice, so we can look at half-life in a more primate-like model, but still doing it in mice. And then as it moves into clinical phases, we can support in terms of material and product, but we do not go into any developments like that ourselves. And with that, I think I'll just stop here, and thank you. And take any questions if you have any, even about neuroscience if you'd be interested. Yes?
Very interesting approach to extend the half-life of the bioactive peptide. I was just wondering, after you make a fusion protein between albumin and the peptide, would the body recognize as antigen? Because it's not a real natural thing anymore.
It's true. And actually so again, when we come into the real immunogenicity and stuff like that, we're usually into the clinical phases, and it's slightly beyond what we do. But we've heard from our collaborators, and it's also somewhat in the literature if you look through, that the main issue is not the albumin bit or the peptide bit. The main issue is actually the bit where they go together, because that is a new entity. So what we've heard is that if you can design that overlap between the two in a way that you actually use something which is already out there, you can actually get around the immunogenicity problem, because you don't have these seams between two different entities that are recognized by the body. What the body normally does is that it cuts up a bit of protein, and then it exhibits them on these MRC8 cells. And therefore, if you have something which is peptide, I know, then I don't know, and then something new comes up, the body will react to that. But if you can somehow make a linker, so you still make it seamless that you go across and you still exhibit something which is known by the body, then you can get around immunogenicity. And then on top of that, actually, albumin has immunogenicity lowering, dampening effect, we can see. It has something called trekitopes in it. So if they're co-exhibited, you can actually lower the immune response to what else is out there. So we haven't had that issues with it yet, but we know that for some, especially the scene between the two, that can be an issue.